So another example of solving a differential by using a power series. So this time we have y prime plus x cubed y equals 0. And this one's going to be a little bit more algebraic intensive than the previous. Let's solve this analytically first. All right, and we can use separation of variables really nicely and easily. And so we're going to get dy dx is going to be equal to the opposite of x cubed y. And we can just clearly separate that into dy over y equals negative x cubed dx, which just becomes ln absolute y is going to be equal to, if we integrate both sides, negative 1/4 x cubed, x4, excuse me, plus c. And then if we go through, we can say that y is going to be equal to plus or minus k e to the minus 1/4 x to the 4th. Alright, so that's our solution. And we can kind of just meld that plus minus k into just make it a k, but that's fine. Alright, so that's what we're aiming for. Now, we're going to make this more difficult on ourselves and use a series. Remember, we always start out with this series, n equals 0 to infinity of c sub n x to the n. It'd be really nice if they told us what c sub n was, because then we'd be done. Y prime, remember we found the derivative in the previous video. We have to bump up the index by 1 to avoid differentiability issues. It's going to be c sub n x to the n minus 1. And we're going to substitute everything back into the original differential, which was y prime plus x cubed y equals 0. And so we know what y prime is. Y prime is the series n equals 1 to infinity c sub n x to the n minus 1 plus x cubed series n equals 0 to infinity c sub n x to the n, which is equal to 0. Alright, now one of the whole reasons that we use a power series when we have coefficients of variables is we can just move the x into the series and combine it with this x to the n. Alright, and then that way we're eliminating the use of that, or we're not eliminating it, but we're actually incorporating it into the solution. Alright, so we have series n equals 1 to infinity c sub n x to the n minus 1 times n plus series n equals 0 to infinity c sub n x to the n plus 3 equals 0, just by some algebra. And you might remember in the previous video, one of our goals is to make the powers of x the same so we can factor those out. And to do that, we're going to use a change of variable. Now, I always pick on the smaller one. Alright, so x to the n minus 1 is smaller. So let's let n equal k plus 4. And the reason we use k plus 4 is because if we add 4 to negative 1, that's going to give us k plus 3. So we're looking to make these exponents equal, so that way we can factor it out. And so we're just going to leave this one alone. So n is going to be equal to k. That is going to give us a little bit of a residual issue. All right, and I'll show you how to take care of that in a moment. So we are now going to have series, and remember, this is going to be that n minus 4 is equal to k. So when we plug 1 back into n, that's going to give us a negative 3. So k is going to range from negative 3 to infinity c sub k plus 4. Instead of this n, we're going to substitute that with k plus 4. And now we're going to have x to the k plus 3. Alright, so it looks like we made things a lot worse. In some respects we did, but at least it's operable now. Now we have the series k equals 0, so we're just substituting n's for k's to infinity. C sub k x to the k plus 3 equals 0. Alright, now, some good news is that the powers of x are now the same. That's great. Bad news, though, is that the indexes are not the same. And we didn't run into that problem in the previous example. In the previous example, they just took care of themselves. So what happens at this point? Okay, well, the trick is that we are going to break off terms to get equivalent lower bounds. All right, so we're going to have to break off enough terms from this k equals -3 to get to k equals 0. So what are we going to have to break off? We're going to have to break off k is -3. We're going to have to break off k is -2, and we're going to have to break off k is -1. So remember, with a series, you just keep going up in terms. All right, so in this case, we're starting at -3, then we go to -2, then -1, and then we hit 0. And all we're going to do is we're just going to substitute those values back in to this sequence, k plus c sub k plus 4, k plus 4, x to the k plus 3. So what happens when we plug -3 back in? So that becomes c sub 1 times -3 plus 4 is 1. X to the -3 plus 3 is x to the 0. We're going to plug in -2. That gives us c sub 2. -2 plus 4 is going to be 2. And then -2 plus 3 is 1. So that's x to the first. And then finally, we're going to plug in -1 into the sequence. And so that becomes c sub 3 times 3 times x squared. All right? Because we broke off -3, -2, -1, we can now start the index at 0. Okay, so to that we can add now the series k equals 0 to infinity, c sub k plus 4 times k plus 4 times x to the k plus 3. And then we still have the series of this series right here, this k equals 0 to infinity, so series k equals 0 to infinity of c sub k x to the k plus 3 equals 0. All right, so how did that help us? Well, what it did was it gave us the same lower bounds, and we have these x to the k plus 3's. Now we can factor out the series. All right, so I'm going to simplify all these c terms, and then I'm also going to factor out. So this is now going to become c1 plus c2x plus c3x, or 2c2x plus 3c3x squared. Those coefficients aren't going to matter that much. Plus, we're going to factor the series, k equals 0 to infinity, x to the k plus 3. And then all we're going to be left with is this ck plus 4 times k plus 4. And then also we have the c sub k from the second series. All right, so this is going to be k plus 4. And then we have this c sub k plus c sub k is equal to 0. All right, so at this point, now we're going to have to use a little bit of not, I wouldn't say trickery, but we're going to have to go through and just process all of this. All right, now one thing that's obvious is that the trivial solution, and remember this is all y equals, right? So that's our solution, so y equals all this stuff. But one solution is when y and x is 0. I mean, clearly if you plug in zeros for everything, then if you have a constant, then it's just going to go away. So x equals 0, that's trivial. We don't care about that. All right. We do have something that we didn't see in the previous example. We have that c1 plus 2c2 plus 3c3, and then we have these x's, is equal to 0. And remember that this is the same thing as 0 plus 0x plus 0x squared. So wouldn't it make sense that the coefficients of x have to match up to the coefficients of x, right? Because truly, if this is all equal to 0, and x can be any number that it wants for the solution, that means that these constants have to be 0. So one thing that we can see right away is that C1 and C2 and C3 are equal to 0. All right, and this is a trick that we're going to use throughout the course when we solve these by series solutions. One last thing that we can arrive at is that we can arrive at the fact that C sub k plus 4 times k plus 4 plus C sub k is equal to 0. So C sub k plus 4 times k plus 4 plus C sub k is equal to 0. And that's our generating function. All right, so in other words, we can write this as C k plus 4 is going to be equal to the opposite of C sub k, divided by k plus 4. All right, so I'm going to stop this video for now, and I'm going to go into another video to where we finish this off, and we go through and we figure out what the generating function looks like for C sub k, and then we can eventually get C sub n and get our solution and then check it. All right, but this might be a good point for you to make sure that everything up to this point makes sense, and then once you are able to resolve that, then you can move on to the rest of this video.